All right, so let's get started. Now, up until now, we have looked at the representation of Bayesian networks, the syntax, the semantics, and one inference procedure, an exact inference procedure. The reason I call it exact is because it will give you the exact probability of a particular query, an exact inference procedure that solves the answers to the queries that you pose at the Bayesian network. Now, of course, we have also studied that Bayesian network inference is sharply complete, which basically means that we cannot hope that it will be solved in practical times for large enough Bayesian networks. And so, it is important that we come up with some kind of an approximate procedure, right. And we are going to study one approximate procedure, one that I am very fond of. Again, it is a sampling based method. So, we are going to use sampling to answer queries in a Bayesian network, and we will get started with a very simple intuition. Okay. This intuition sort of is not exactly appropriate for the task at hand, but it will give you a good starting point. So, suppose I want to estimate probability of heads for a coin whose probability is unknown, okay, and we can hope that maybe it is biased, we do not know that. Now, if we are in such a situation, then we have to estimate probability of heads, we do not know the probability, but we are given the coin. What are we going to do? Toss it many times, take lots of samples from the coin, and then say out of the total number of tosses, what fraction of times did I get heads, and that would be my estimated probability of heads, right. So, to estimate any probability, right, we can sample, we can take samples, we can take help from samples, and we can use some kind of a fraction to compute that particular probability at hand. Okay. So, this is a very general concept, right. To estimate any kind of probability, we can use sampling. And of course, when will I get the correct probability? The obvious question. When will I get the correct probability for this? When I sample lots and lots and lots of times, in the limit the number of samples tend to infinity, right. So, we now know that we now have a simple approximate procedure to sample probability of heads. Suppose probability of heads is 0.5. Am I going to estimate 0.5 in a say 10 samples? Maybe, maybe not, right, unlikely. You might have 6-4 split, you might even have a 7-3 or 8-2 split by some chance. You might also have a 5-5 split, but you have to be very lucky to have that. So, this would be an approximate computation, but after this approximate computation, as we keep increasing our number of samples, the probability will tend closer and closer to 0.5, right. You might have a million samples for heads and a million 100 samples for tails, and so on and so forth. Okay. Now, Bayesnet inference, what we have been doing, this is really a learning problem. We are learning the probability of heads by trying it out. So, technically Bayesnet inference is not a learning problem, but the same intuitions are going to apply. In particular, like we can sample a coin, believe it or not, it is very easy to sample from a Bayesnet, and these samples will be unbiased or can be unbiased if you try, right. So, now what is the meaning of bias in sampling? Let us first make sure we understand that. So, bias or unbiased samples are those samples which are representative of the world, right, or in this case representative of the Bayesian network. For example, suppose I want to estimate the total probability of people greater than 60 years of age living in Delhi. This is my goal. We want to estimate probability of people greater than 60 years of age living in Delhi. What fraction of the people who live in Delhi are greater than 60 years of age? Now, suppose I come to the computer science class and I just check how many of you are greater than 60 years of age, and deduce that the probability is 0. Even I am not 60 yet, even though I may look like one. So, then I deduce that, oh, because in the computer science class there is nobody 60 years of age, so therefore probability is 0. Would this be a biased sample or an unbiased sample? Very biased sample, right? I could call on a landline. Would this be less biased? Probably less biased, but would it be biased also? Why? Why did you say it is going to be biased? If you are really calling random people, then what? It won't be biased. So, Purva says it won't be biased. Somebody can tell me why it would be biased? Yes, Ishan? Children under 5 may not be picking up the phones. Very good. Another reason it might be biased? If they are using landline, then there is a higher chance they are old, because the youngsters don't use landlines anymore. How many of you have a landline at home? See, very few, maybe less than 50%. If you had asked this question 10 years ago, everybody would have raised their hand. So, almost everybody. Then there is a rich poor bias, right. A lot of people who may not have any phone or at least a landline phone are people who do not have a steady home or do not have a home which has connected landline phones. You can call on a cell phone. That might have another kind of bias. People may have started living in Delhi, but they have moved to Bangalore, right, or things like that. You can check their Facebook pages. That is probably less biased. We know all the old people are now on Facebook, which is why none of you are. Where are you guys these days? Instagram? That is what I have been told. If you are still on Facebook and not on Instagram, think about your age. Okay. Or you can do a count at election booth. Whatever kind of sample you choose, it is going to be biased. That is why all these people, do you remember when Arvind Kejriwal government was not formed and people were doing these exit polls? I do not know if you remember, this is 5 years ago, almost 5. Almost half the people predicted that BJP is going to win, half the surveys predicted that AAP is going to win, but the margins were very low. And then Kejriwal ended up getting 67 out of 70 seats. Why? Because they were doing some kind of a bias sampling. And in that particular case, their sampling became too biased that the people who came for voting and the people who were responding to exit polls became too different. Anyway, because we are in the Bayesian network world, the good news is that we can actually deal with bias explicitly. So, this is just a general idea of what does it mean to have a biased sample and an unbiased sample, but we are given the model of the world, and the model of the world is the Bayesian network. Because we are given the model of the world, we will just focus our energies on sampling from the network itself and not worry about many of these real world problems. Now, of course, the model of the world may be wrong. The Bayesian network itself may be wrong, but that is okay. We have approximated things out, we have abstracted things out, all models are wrong, but we believe that the Bayesian network given to us is useful. So, we are going to work with the network that we are given, with the conditional probabilities that are given to us. However, they may have been estimated, they may have been errors in the estimation, we are not going to worry about that particular bit. Okay. Now, the good news is I am going to mention or introduce a new term, not in detail. If you take my NLP class, we will spend like 3 or 4 lectures just talking about these two types of models. One is a generative model and one is a discriminative model. I am surprised somebody knows this, right, in this class. So, a discriminative model cannot generate samples from the distribution, but a generative model can generate samples from the distribution. Okay. So, Bayesian network is a generative model. You can easily, in fact extremely easily generate samples from the distribution represented by the Bayesian network, and Bayesian network represents a joint distribution, right, always. And what is the algorithm? The algorithm is super simple, generate one variable at a time in topological order. That is it. Let us look at an example. We are going to use this running example, burglary, earthquake, alarm, and let us say John and Mary is not separate anymore, there is one neighbor who calls or does not call, and then let us say there is something on the radio or the newscast which tells you whether there was earthquake or not. So, we are going to use this particular running example, and we are given these conditional probability tables, and what we are going to do is we are going to just sample from the distribution. What does that mean? We will toss a coin with probability 0.03, we will say burglary is true, and with probability 0.97 we will say burglary is false. By the way, how do you toss a coin such that it gives you two things with probability 0.03 and 0.97? Again, this should be obvious to people who actually do some coding in life, but for others, how do you toss a coin in any programming language? What function do we use? We use the rand function. So, the rand function always gives you a number between 0 and some rand max minus 1, right. And so, we can take this dividing line and that we can say that okay, our total length is rand max and 0.03 into rand max is one side of the coin and 0.97 into rand max is the other side of the coin. So, we have gotten our threshold. So, we sample a random number between 0 and rand max minus 1, we assume that it is a uniform sampling, and then we say whether it is less than the threshold or greater than the threshold, and that gives us the result that we want. So, random number generators always give us a uniform sampling. These are pseudo random. So, they are expected to give us uniform sampling, and then we use the uniform sampling with the right thresholding to give us the probability that we want, right. So, these things you have to be careful of. Okay. So, we toss a coin with probability 0.03, we figure out the value of burglary. We toss a coin with probability 0.001, we figure out the value of earthquake. Now, that we have the value of burglary and earthquake, the alarm probability is determined by one of these four values, depending upon whether burglary and earthquake were true, burglary was true, earthquake was false, or what was going on. And then let us say burglary was false, earthquake was true, then we toss a coin with probability 0.4, and that tells us whether actually alarm goes off or not. Now, based on the probability of alarm, we figure out whether somebody called us or not, and so on and so forth. So, in other words, we have done these small probability flips, and at the end of all the flips, what do we have? We have one sample from the joint distribution. B is false, E is true, A is true, C is false, E is false, whatever. That gives us our one sample. Now, we can do these coin flips many times, and we have got lots of samples. And notice each sample is generated by the joint distribution. So, these are real samples, real means these are simulated samples, but from the distribution that the Bayesian network represents. And therefore, we can use these samples to compute any kind of a marginal probability. Let us say we want to compute probability that somebody is going to call us without anything, any evidence. So, we can just check in how many samples was C true and what was the total number of samples, and that gives us the probability that somebody is going to call. I want to pause here. Is this okay for now? It is like the same thing. How do we compute probability? We sample or toss the coin many times, see how many times we get heads. In the same way, a Bayesian network represents the joint probability distribution. So, we sample from the joint. What is a joint sample? A joint sample is each value filled up. So, we sample it. Now, we want to estimate the marginal probability of somebody is going to call, then in some samples call is true, in many other samples call is false. So, we take the total number of samples in the denominator and the number of samples where call is true in the numerator, and that gives us the marginal probability that somebody is going to call. Okay? Any questions? If you did not understand this, then the whole next part of the lecture is going to be hazy for you. So, if there is any question, this is the time to ask. Yes?
Sir, could you once repeat how we generated one sample?
How do we generate a sample? That is the question. How do we generate a sample? We go in the topological order. We start with the node which has no parents. Now, its value can be determined by an independent coin flip, right. So, for example, whether burglary is going to happen or not, we can toss a coin with probability 0.3, there will be burglary, and 0.97, there will not be a burglary. Similarly, earthquake, we do the same thing. Now, in this sample, burglary has been determined and earthquake has been determined. That is what has happened so far. Will alarm go off? That is determined by the specific conditional probability based on what values we have sampled for burglary and earthquake. So, let us say we sample that burglary happens, but earthquake does not happen. So, then we will toss a coin and with 0.7 probability alarm will go off, right. So, we are estimating the various possible worlds that can happen with the Bayesian network, but not only are we estimating them, we are estimating them such that the world that is more likely will happen with a higher probability, right. That is sort of the point. Okay. So, now the more interesting question obviously is how do we compute, let us say we get a call, the probability that burglary happened. How do we estimate probability of B given C? Okay. Any suggestions? So, let us do again the thought experiment. You are standing in Connaught Place, you are interested in what is the probability that a person has a master's degree given that their age is greater than 60 years. Okay. What is the B given C, right? What is the probability that they have a degree, graduate degree, postgraduate degree or more given that their age is greater than 60 years? What do? You are standing in Connaught Place, what do? You go to a random person and first ask, what is your age? Is your age greater than 60 years? What is your name? Cheyenne. So, Cheyenne says, is your age greater than 60 years? That is the first question I will ask. Now, if the age is not greater than 60 years, what do? You just ignore this person, yeah, you are not useful to me, please go away. We reject this sample. If we are interested in probability of B given C and C is false, that sample is not useful to us. We reject the sample. However, if their age is greater than 60 years, then what do we ask? Do you have a master's degree? And if they have a master's degree, we increment the numerator by 1 and either way we increment the denominator by 1, and that gives us the probability. Now, if we want to compute probability of burglary given that we are going to get a call, what do we do? Given that we got a call, sorry. Now, you have the intuition. What do? We take, so Vaibhav says, let us sample from the joint distribution as we were doing in the last slide. And now, what do? There are some samples when call is true and there are some samples where call is false. What do? We reject all the samples where call is false. And guess what is this algorithm called? It is called rejection sampling. Engineers do not have very creative minds when it comes to naming an algorithm. By the way, there is a trick to naming your algorithm. You have to make sure that the name is funny or at least catchy, and you have to make sure that it does not exist in Google with something else. Like one of my students have named our latest data set carb. Now, that is interesting as a name, but as soon as somebody searches carb, they are going to go everywhere. The amount of carb deposits and global warming and all of that jazz. Terrible name for a system. So, when you ever get to a point where you have to name a software or in some cases name a system that is a research prototype, always work very hard on naming it. You have worked 1000 hours in coming up with the algorithm, please spend 1 to 2 hours in naming it right. Alright, so that is exactly what you do. You start sampling, you get one sample like your first sample B, B was false, your next sample E, E was true, your next sample, now B is false, E is true, so you are going to use the probability 0.4, your next sample A, let us say A is true, so then you next sample C with probability 0.8 because A has been true, you get C, then you next sample N with a probability 0.3, you get N false. Now, is this sample relevant to you for probability of B given C? Yes, this is relevant to us. Similarly, if we get this other sample, is this relevant to us? No, we do not care for this. So, we get rid of this. And so, then we want to finally compute probability of B given C, that can be computed as number of live samples where the burglary was true given that total number of live samples. We have already rejected all the samples where C was false. This is called rejection sampling.